Welcome to a code report solution video. In this video, we are going to solve a LeetCode problem in BQN and Haskell because this one is fun to solve in BQN and it's interesting to see the equivalent solution in a more functional language like Haskell. So this is problem number 1 from the most recent LeetCode contest. If you're watching this video when it comes out, which I believe is contest number 234. I could be wrong about that though. The problem is entitled Left and Right Sum Differences, and it actually has a pretty confusing problem statement. It says, given an zero-indexed integer array nums, find a zero-indexed integer array answer where the length of answer and nums is the same, and the result of the answer is equal to this. It's the left sum, whatever that means, minus the right sum, and the absolute value of that. And basically, if you read this, left sum and right sum are left and right pre-scans, which I'll explain when we look at BQN. Or I guess I can explain it right now. So if you look at 10483 as our first example, the left sum is a left plus pre-scan, which means you're basically doing a partial sums, but the pre-scan part means that you sort of have to initialize the first element to 0. So first you have 0, then you have 0 plus the first element 10, which gives you 10, then you have 0 plus 10 plus 4, which gives you 14, and then you have 0 plus 10 plus 14, 0 plus 10 plus 4 plus 8, which equals 22. Note that technically a pre-scan should have n plus 1 elements. So if we have 4 elements, it should result in 5. But in this case, left sum defines it to be only the first 4. So it drops the last element from your plus pre-scan. And there's a second example with just a single element 1, which is uninteresting. Let's hop over to BQN pad and solve this there. So here we are. The solution on LeetCode gives you the function name left-right difference, and we have our 2 examples. Note that we're only showing the second one because the way BQN pad works is that it only shows the last expression. But if we do the following, we do the dot show, that will basically print out a non-last expression. And so let's solve this problem. First thing we need to do is let's do the left sum first. So this is a plus scan. So we've got our plus binary operation and our scan privative. So you can see down here, we basically got 10, 14, 22, 25. And that's basically what we want, but we need to do what's known as either am I going to know how to type this? What's the negative? Yeah, -1 and then drop. If I can remember. There we go. So, and technically we would also need to append here, but this is kind of overly verbose. So in BQN, there is something called, I believe this is the right shift. I could be wrong about that. But this is going to basically shift everything to the right and then add the identity value or the default value for our type, which is 0 in this case, which works out perfectly. So this is basically our left sum. And so now we need to get our right sum. So let's create a fork here. And catenate will be our binary operation. So for now, if we do this, basically what this is saying is catenate our left sum with the identity of x, which is just our regular array. So now if we start building up our right sum here, we'll get the following. So this is our plus scan. In order to make this a right scan, though, we can use the absolutely magnificent operation called under. And if we combine that with reverse, this is basically the equivalent of a right scan. And now we just need to use the sort of sibling function to a right shift, which is left shift. And if we do that, then we basically should have here our right sum and our left sum. And so all we need to do now is basically replace this catenate with a minus. And then at the very end of this, absolute value everything. And if we check back with our LeetCode solution, 15.1.11.22 is the correct answer for this problem. And because of the way that I've written this, we can actually very conveniently turn this into a point-free solution because we already have basically a B combinator, aka and a top combined with a fork here. So we can just go delete, 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 come over here and go delete, delete. And look at that. Poof, beautiful. We just deleted like 5 or 6 characters, barely changed anything. And that is our solution in BQN. Absolutely beautiful. This under here, one of my favorite things, is top 5 things about BQN that other array languages, actually J does have this, but APL does not. So it is one of the top 5 things that BQN has that some other array languages do not. And this left shift and right shift are also quite convenient compared to doing like a -1 drop and then concatenating a 0 at the front. All right, that is the BQN solution. Let's hop over to our Haskell interpreter and solve the solution there. All right, here we are in PowerShell. I have loaded up our GHC interpreter for Haskell, and I believe, what was it? 10.4.8.3, I believe, was our list. So let's start once again by doing our left sum, which is going to be scan L. If we do the 1, we don't have to specify an initial value. But in this case, we actually do want the pre-scan. So this is the scan algorithm. If we get rid of the 1, that is the pre-scan algorithm. So we can specify an initial value, and that gives us the 0, 10, 14, 22 we want. Note, again, we need to do some kind of shift operation. Very conveniently in Haskell, we could do a like a take 4 kind of thing, but really what we want is we want that kind of drop -1, drop the last element. And there is actually a convenience function in Haskell called init, which gets rid of the last element. So perfect. This init dot, which the dot here is the B combinator, scan L plus 0 is what we want. In order to get the right sum, we basically just need to change init to tail, which means drop the first element. But before we do that, let's just change the scan L to a scan R. So this is going to just do the exact same thing, but scanning from the right instead of the left, which is basically the equivalent of what we're doing with under. We don't need to use under reverse because we have 2 different scan algorithms, left and right, in Haskell. So now, once again, we could do the drop 1 in this case, but as I mentioned before, there's a convenience function called tail, which is the exact same thing as drop 1. So now we have our init.scanl plus 0, and we've got our tail.scanr plus 0. So now what we need to do is basically subtract these 2, which was just a single operation, a single minus in BQN. The equivalent of trying to do things with 2 different lists is zip with. So we go zip with, and then I guess we're doing left scan. So it doesn't really matter which order because we're going to have to do the absolute value, but it would be something like this. Init.scan L plus 0. However, this is not going to work because what we're actually doing here is we're passing our argument at the bottom here, 10. I wonder if can I clear this? I cannot clear. Oh, well. I need to pass this 10.4.8.3 to the 2 different operations, the init scan L and the tail scan R. And so the way we did this in BQN is with a fork, aka the phi combinator. So the thing to actually do here is to go let phi, and then we'll go A, B, C, where A is our binary function and B and C are our 2 unary functions. And then we go A, BX, CX, and this is the phi combinator. So now if we go back here and we go phi and then put this in parentheses, delete this, now we should get the correct answer. And all we need to do now is go map absolute value with the B combinator, and we're good to go. However, there's actually, I'm not actually sure, do we have import data.composition? We do. And so we can actually, I prefer this. We can use the B1 combinator. So if we put this in parens and then we go absolute dot colon, this is the B1 combinator, and this is saying basically apply this unary operation after this binary operation. So we're subtracting the 2 lists from each other and then taking the absolute value of each element, which is quite nice. So if we do this, we have our solution. So now I'm going to hop over to a nicer version of this to compare the BQN and Haskell solutions. So this was our first Haskell solution, phi combinator, zip with minus for our binary operation, and then doing a tail scan R and a init scan L to get our two sequences. And after we perform all that, mapping the absolute value. But as I mentioned, we can fold the absolute value into our zip with if we make use of the B1 combinator. And if we juxtapose this with the BQN solution, we can see that these are both extremely beautiful. BQN has the under operator, which enables us to get the right sum, aka a right scan. We don't need this in Haskell because we have two different flavors of scan, scan R and scan L. We have the two different shifts in BQN, which we can get that behavior using a pre-scan for both of our scans, and then the tail and init functions. The minus in BQN, obviously a lot easier to spell than having to use a zip with because we don't have rank polymorphism in Haskell. And each of these solutions are using the phi combinator, which is what we call a fork in BQN, and the B combinator. The B combinator is the dot in the Haskell solution, and it's implicit in the BQN solution when we compose the absolute value function with the unary function that is returned by our phi combinator or our fork. And yeah, absolutely beautiful. The B1 combinator also in Haskell. We could use the B1 combinator in BQN if we moved our absolute value from the leftmost character into the middle next to the minus, and then we put the B1 combinator in between that, which is the jot operator. But yeah, BQN, Haskell, both two of my favorite languages. BQN's my favorite language. Haskell is number 3 or 4, and absolutely awesome languages if you're interested in combinator programming. Stay tuned on this channel for my talk, Composition Intuition, which I'll be uploading sometime in June as I'm giving it at a conference early June in Poland. Thanks for watching. I hope you learned something. I hope you enjoyed, and have a great day.